Hello, and welcome to episode 11 of Maths in an Empty Classroom with me, Mr. Southern. Today we're looking at the second example on vector kinematics non-constant acceleration. What we learned when looking at example 1 was that you apply calculus in the same way as you would if it was not in vector form, but you treat the I component and the j component separately. So here we have a second example with a little bit more going on. So a particle P moves in a plane with an acceleration of 2t j meters per second. At time t equals 0, the position vector of P with respect to a fixed origin O is I plus 4j, and the particle P has velocity 3I minus 4j. So I'm just going to go on to the next screen and just jot those things down because I'm going to be using them very shortly. So we were told that the acceleration was 2t j, and we were told that at time 0 the position is I plus 4j and the velocity is 3I minus 4j. Okay, so I plus 4j and the velocity 3I minus 4j. I'm just going to check that. I plus 4j, lovely, cool. Okay, right, and in part A we're asked to find an expression for the velocity of the particle at time t seconds. Now there's something that can potentially trip us up here. We should be happy from doing the first example that velocity is the integral of acceleration with respect to t. Now, if we are going to integrate 2tj with respect to t, we don't have an I component, but we still have to integrate the I term. So what happens is we actually just get a constant of integration for I, and then we integrate the j bit and we get t squared, excuse me, j, when I've forgotten the second constant. So plus c2 j. Okay. So we're told at time 0 the velocity is 3I minus 4j. So we can substitute that information in. So when t is 0, v equals 3I minus 4j, which means looking at the I components that c1 equals 3, and when you substitute in 0 to t squared, you obviously get 0, so it means that c2 would equal negative 4. And therefore an expression for velocity at time t seconds is 3I plus t squared minus 4 j, and that is in meters per second. So the next bit, find the position vector of P at time t seconds. Okay. So for position vector, we're going to be integrating the velocity. So position vector, which I call x, is the integral of velocity with respect to t. So if I integrate the i's and the j components separately here. If you integrate 3, you get 3t plus c1. It doesn't matter that I'm calling it c1 again, it's a different question, a different constant. I'm going to find it as a number in a moment anyway. I get plus 1/3 t cubed minus 4t plus c2 j. And that is my expression for position. I was given in the question that the initial position when t is 0 was I plus 4j. So when t is 0, x equals I plus 4j. Substituting 0 in here, I get 0, which tells me that C1 equals 1. Substituting 0 in here, I get that C2 equals 4. And therefore I can express the position of P using the equation x equals 3t plus 1I plus 1/3 t cubed minus 4t plus 4j. And because that's position, that's in metres. Part B, position vector, done. Right, part C is asking me to calculate the displacement of the particle. Now, displacement is how far it's moved in relation to where we started. And there's two approaches we can take to this. I'm going to take you through both of them. The first one is we need to find the position when t equals 3. And the way we do that is we substitute t equals 3 into our position equation. So x equals 3 lots of 3 plus 1 for the I component, and substituting 3 into the j component, 1/3 3 cubed minus 4 lots of 3 plus 4j, which gives me that the position after 3 seconds is 10I 9 minus 3 plus j. Now, that is not the same as displacement. That is where it is, not how far it's travelled. What we have to remember is that our initial position was I plus 4j. So, initially, or our initial position, was I plus 4j, and we want to know how far we've moved in relation to that initial position. So if we started at I and we're now at 10I, then the displacement, which we'll call S, must be 9 in the I direction, doing 10 minus 1. Similarly, if we started at 4j and we're now at j, we must have minus 3j as our displacement, and that is in metres. So that's one way of doing it. If you're asked for displacement, find your position and check to see where you started. Where are you in relation to that? Because we started at I plus 4j, we had to subtract that vector from our current position. The alternative to that is you can work out displacement by doing definite integration. So you'll remember that we integrated velocity to find out displacement. You could integrate the velocity with respect to t for the first 3 seconds of motion. Now, remembering that our velocity vector was 3I plus t squared minus 4j. So 3I plus t squared minus 4j. And we're doing that with respect to t. So we're going to get 3ti plus 1/3 t cubed minus 4t j between 3 and 0. You probably recognise quite a lot of what's appearing on screen at the moment. So if we substitute in 3, we'd get 9i. Substitute 3 into here, we're going to get negative 3j. And if we substitute in 0, we're going to get 0 from both components. So you can see that what we've arrived at is 9i minus 3j meters, which is the displacement in the first 3 seconds. So how far it's gone in relation to where it started. And how you approach this is up to you. In this scenario, my preference is to say, well, sub in t is 3 because we've already integrated it, and then work out where it is in relation to where you started. If you hadn't already integrated it and you didn't have an expression for its position, then you could integrate velocity, do it between the two limits, and the bonus of that is you don't have to find the constants because you don't actually care about either position, it's about how far it's travelled, where it's gone, which is what you worked out here. Lovely. Next bit then, the distance of the particle from the fixed origin O after 3 seconds. Now the fixed origin O is the origin, it's 0, 0. So this is when we do need to use the position of the particle. The whole purpose of this example is to examine, do you understand the difference between position and displacement? So the position when t equals 3, we worked out in part C to be 10i plus j. But that is a position, it's not a distance. To turn that into a distance, which is a scalar quantity, we're going to have to crack out Pythagoras, turn it into a magnitude, which is the square root of 101, which is going to be about 10, isn't it? Let's be honest. 10.04, so it's 10.0 metres to 3 significant figures. So we needed its position because its position vector will always be relative to the origin O, 0, 0, not its displacement. That was something different that we worked out in part C. And finally part E, when t is 2, p is at the point A, when t is 5, p is at the point B. Now this is talking about position, so what I'm going to do is I'm going to substitute t is 2 into my position vector, and I'm going to substitute t is 5 into my position vector. So my position vector was the x1 that I worked out here, 3t plus 1i, plus, I think it was 1/3 t cubed minus 4t plus 4, yes it was, so it's 1/3 t cubed minus 4t plus 4 j. Right, when t is 2, I get 7i, and when I put t in here, I get 8 over 3 minus 8, so negative 16 over 3, so I get negative 4/3 j. We'll just check that. 8 over 3 minus 8 plus 4, negative 4/3. Yeah, lovely. Okay. When t is 5, substituting t is 5, I get 16i. Substitute t is 5 in here, I'm going to get 125 over 3 minus 20 plus 4, which is 77 over 3, so plus 77 over 3 j. That has found me the position A, and that has found me the position B. And I'm being asked about the vector A to B. Now for a to b, we're going to do b minus a. So that is going to give us here, if I do this one, take this one, it's going to give me 9i. If I do this one, take this one, 77, take negative 4, 81 over 3, which is 27. Okay. And I was asked to show that the magnitude of a to b was 9 root 10. So the magnitude of a to b, crack out Pythagoras, 9 squared plus 27 squared, all square rooted. I'm pretty confident, but I will just check it. Yeah, 810. Root the answer. You get 9 root 10. As required. So, key things you need to be comfortable with. What is position? What is displacement? Position is where we are. Displacement is how far we've come. You're going to have a number of equations to choose from. Just take your time and make sure you're substituting your values into the right one. Job done.